Voilà, mesdames, messieurs, bonsoir ou rebonsoir pour ceux qui étaient déjà là hier soir pour cette première conférence du Colloque Wright. Ce soir, c'est la deuxième conférence. Bienvenue à tous. Comme chaque année, vous le savez, on a le grand plaisir, le privilège même, d'accueillir ici à Genève, à l'université, des présentateurs, des orateurs du monde entier sur une thématique qui est choisie par la Fondation Wright, des orateurs bien sûr exceptionnels. Ce soir, cette année, ne fait bien sûr pas exception. Vous avez vu le programme. Hier soir, il y avait salle comble pour la première présentation. Ce soir, la salle est très bien remplie également. Cette année, le thème qui a été choisi est le thème de la gravitation. C'est une thématique qui va nous suivre durant toute la semaine. La gravitation, la force de gravitation que vous connaissez bien sûr tous, celle qui nous empêche de nous lever le matin, celle qui gère jusqu'à notre posture du corps, celle qui sculpte tout l'univers. Mais celle aussi qui reste bien mystérieuse à maints égards. La preuve, il y a quelques semaines, une expérience en Chine a tenté à mesurer deux valeurs différentes de la fameuse constante de gravitation grand G, si vous vous souvenez de vos cours de physique de base. Donc ça montre à quel point il reste beaucoup de choses à découvrir autour de cette force de gravitation. Cette soirée, comme vous le savez, se déroule en deux étapes. Tout d'abord, la présentation par l'orateur de ce soir, qui durera à peu près 3/4 d'heure, 50 minutes. Elle se fera en anglais. Et ensuite, une discussion durant laquelle nous aurons le plaisir d'accueillir aussi deux autres orateurs de ce colloque Wright que je vous présenterai tout à l'heure. Une discussion qui, elle aussi, se fera en anglais, mais vous avez dû recevoir toutes et tous un casque de traduction simultanée à l'entrée pour l'écouter en français et aussi pour poser vos questions en français ou en anglais. Elles seront traduites aux orateurs qui seront sur scène avec moi tout à l'heure. Une petite consigne d'usage, vous la connaissez, de ne pas éteindre votre portable. Pourquoi je dis ça? Parce que je vous demande simplement de le mettre sur mode avion, parce que vous aurez l'opportunité aussi de poser des questions par Twitter à travers le hashtag que vous avez là, Colloque Wright. Et ces questions seront ensuite relayées sur la scène par une personne qui m'aidera durant la partie de questions-réponses. Ça nous sert aussi à toutes celles et tous ceux qui nous suivent en direct par Internet devant leur écran d'ordinateur. Donc à elles aussi, vous avez l'opportunité, à travers le hashtag, encore une fois, sur Twitter, de poser vos questions en français ou en anglais aux orateurs de ce soir. Voilà, sans plus attendre, pour entrer dans le vif du sujet, je passe tout d'abord la parole au président de la Fondation Wright, Thierry Courvoisier, pour quelques mots d'introduction.
Merci, bonsoir. C'est un voyage magnifique que la Fondation Wright vous convie ce soir. Un voyage qui, s'il n'avait pas obéi aux lois de la gravitation, passerait pour magique. Andrea Comazzo ne le dira peut-être pas, mais l'Agence spatiale européenne a réussi avec Rosetta une des plus belles missions spatiales qui ait jamais été conçue et réalisée. Un voyage dans notre système solaire pour atteindre une comète, se mettre en orbite autour et faire atterrir une sonde dessus. Une merveille d'ingénierie pour des résultats scientifiques de tout premier plan, exploité entre autres par Catherine Altweg à Berne, que vous entendrez dans un moment. À vrai dire, tout ceci est bien au-delà, pour poursuivre notre lecture de Tintin, de la mise en orbite du capitaine Haddock autour de l'astéroïde Adonis entre la Terre et la Lune. À vrai dire, là, une incohérence physique et astrophysique. Je suis très reconnaissant et heureux qu'Andrea Comazzo ait trouvé le temps de venir partager le récit de cette réussite avec nous. Il est en effet maintenant responsable des opérations de vol d'une autre mission interplanétaire lancée il y a quelques jours seulement, Bepi Colombo, du nom d'ailleurs de la personne qui a inventé cette technique qui consiste à faire un espèce de billard spatial pour aller se promener dans le système solaire avec un peu plus de facilité que simplement avec le carburant qu'on a emmagasiné dans son dos. Donc c'est lui qui porte ce nom Bepi Colombo, qui est à l'origine de la méthode utilisée par l'Agence spatiale européenne et les autres agences pour se promener vers des planètes ou des comètes, comme il nous le racontera. Anyway, il est responsable des opérations de vol de cette mission et malgré ça, il a trouvé le temps de venir passer avec nous une partie de la semaine et je lui en suis extrêmement reconnaissant.
Voilà, merci beaucoup Thierry Courvoisier. Allow me now to switch to English because the conference and the talk will be in English. To present our guest tonight. Actually, I will not present it. I will ask someone to come on stage, a very special person, because this person not only knows Andrea Comazzo very well, but she had to actually have an infinite confidence in him for 10 years, and I'll explain why. This person is Katrin Altweg. She's an honorary professor of physics at the University of Bern, and she was the principal investigator of an instrument. It's a gas spectrometer that was on board the spacecraft Rosetta. And actually, what she definitely must have hoped for 10 years is that the spacecraft was brought to destination really safely and actually would just awake, because Andrea might tell it afterwards, but the spacecraft was sleeping for most of the voyage. So, Katrin Altweg, now the floor is yours. Thank you very much.
Thank you very much. Thank you very much for inviting me. It is a pleasure for me to introduce Andrea Comazzo. The history with Andrea and myself goes back a very long time, to 1999, when I first saw him in a Rosetta meeting. He just had joined the European Space Operations Center in Darmstadt. At that time, it was before launch, we were still very optimistic that everything would go okay. The closer you get then to the mission, the more afraid you become. Andrea was actually born almost as a Swiss, just on the other side of Saas-Fee in Domodossola. He was at the Academy of the Italian Air Force in Pozzuoli, where he got his basic flight training, not for spacecraft, but for airplanes, I assume. But then he graduated in aerospace engineering in Milano. From there, he went to Fiat Avio, first in Rome and then in Torino, where he had the first contact with Rosetta. Actually, it was not really Rosetta. It was just the legs of the lander of Rosetta. But then, fortunately, he joined the European Space Operations Center in 1999, and he worked on Rosetta for most of the period of the flight of Rosetta, with a short deviation to Venus Express, but then back to Rosetta, because, of course, that was the best mission of all. Andrea is a very exceptional person. You know, in ESA there are a lot of excellent engineers. And in ESOC there are a lot of excellent engineers, and they have only one goal: fly the spacecraft safely. It doesn't matter if there is science or not, as long as the spacecraft is safe. And on the other hand, you have the scientists, and they want to get out as much as possible their science, independent of the spacecraft. They don't think about spacecraft, and the engineers don't think about science. And Andrea was actually the only person who could bring this together. We fought a lot, not between us, but against other forces, people who wanted to play safe, who didn't want to take any risk with Rosetta, but he was always very sensible. He kept in mind that we wanted to do science, and he wanted to have the spacecraft safe, and he always took some risks, but never too many. And that's very, very rare. And I'm still extremely grateful for what we achieved, because our science would not have been possible without Andrea. So thank you, Andrea, for this. And please come to the floor.
Well, first, thanks a lot. Catherine has been very generous in describing me like that. But you can imagine that you can achieve such an objective, embark on such an endeavor, not alone. There was a large team behind my shoulders, actually. They were actually pushing me up, and they were doing most of the work. I was maybe in the position to make the final decision, which is not easy, but sometimes it helps to have a large team, competent team behind you. What I'm going to talk to you about tonight is actually about I will use a bit the history of the mission to deal with a specific topic, which is gravity. And actually, the title given to this talk is Mission Zero Gravity. We will actually see that there's not zero gravity, but there's much more than gravity in the Rosetta mission. So the Rosetta mission was a mission to a comet. For people that are less familiar with comets, what are comets? Where are comets? Well, there are billions of comets in our solar system. Actually, they lie outside what we normally consider our solar system. We only think of the solar system as our planets, the planets we know. Well, the solar system goes well beyond. The comets actually reach the interstellar space that is between our solar system and the next solar system. They actually fly or float in a region where gravity is almost absent. It's not absent, technically speaking, but basically they have a chaotic motion in this region. This is the Oort cloud. Far out there, there are billions of comets. Some of them start being trapped in the inner part of the solar system, closer to our planets. Then there are comets that actually fall much more inside the solar system. And these are the comets we can actually reach. This is one we decided to go to one of these comets. Why? Well, because we can reach this comet, we cannot reach the ones which are further out, but also because comets, our scientists tell us that they were believed to be, at the beginning, I use the past, because they were believed to be the remnants of the formation of the solar system. In reality, thanks to Rosetta and people like Catherine and these scientists, maybe we understand that they are not the remnants of the formation of the solar system, but maybe they were there before. So this is what they have created or formed or contributed to the formation of the solar system. So this is what the mission is about. And actually, we're going to see how we flew to this comet and how we flew mainly around this comet. So what is Rosetta? Rosetta was a spacecraft. You can see this on the left image, relatively big. It's more or less like a telecommunications spacecraft. It was 3 meters tall, 2 meters deep, with huge solar panels, 32 meters wingspan. So it's almost like an aircraft in the wingspan of these big solar panels, because we had to fly far away from the sun. The Rosetta name was given exactly like the Rosetta Stone you see in this chart here, because as the Rosetta Stone allows us to understand ancient languages, to understand something that was in the past, so the Rosetta mission was supposed to give us the hints to understand how the solar system actually formed. But what are we doing actually when we talk about space flight? Well, we don't do anything else than playing with nature. Also, these people are playing with nature. They actually use the wind as a force and acceleration by orienting their sail on this boat, and actually to drive or lead their boat where exactly they wanted. Also, when we go skiing, I'm a passionate skier. Also, we play with gravity. Skiing is nothing else than a controlled fall towards valley. I will tell you at the end of the presentation when this person is skiing on. But this is what we have been doing for Rosetta. And Rosetta took 10 years, actually, to fly to the comet. We'll see tonight why it took us 10 years. Many people are obviously think, oh, it's the distance. Yeah, okay, it plays a role, but it's mainly something else. So we launched in 2004. The mission was approved ages ago, in 93, but was even conceived in 85. So a very, very long story. We flew for 10 years in the solar system just actually to match the orbit of the comet. This is what we wanted to do. There were past missions that flew next to comets. We actually wanted to do more. We wanted to rendezvous with a comet, actually fly around with a comet, orbit a comet, and even land on a comet. So gravity all played an important role in this flight as any space flight. So we did several so-called planetary swim-by to accelerate the spacecraft to the level where we could reach the comet. We could match our orbit with the one of the comet. These planetary swim-bys are also called sometimes gravity assist maneuvers. And we'll see that, in my opinion, this word is somehow misleading, and I will tell you why. Finally, in 2014, after having spent many, many years in the solar system, we reached our comet. During the largest part of the orbit you see here on the bottom left of this chart, actually, we had to almost switch off the spacecraft. We were flying so far away from the sun that our big solar panels were not enough to produce all the energy we needed to keep the spacecraft active for almost 3 years. We had no radio contact at all with the spacecraft. We let the spacecraft flying alone in space. Again, many people ask me, how did you know where it would come out? Well, this is driven by gravity. Gravity drives the flight path perfectly. So we knew exactly where Rosetta was coming out on the 20th of January 2014, and we found the spacecraft there, ready to fly to the comet. But how does it work? How could we do all this exactly? Well, this is again another projection on a plane of the trajectory of Rosetta in the solar system. You see the yellow dot in the middle is nothing else than our sun. So our problem was that we were starting from the Earth. It's the blue orbit around the sun, and the green one is the orbit of the comet. So we had to fly from one orbit to the other one. Here we are talking about energy level, orbital energy. The Earth is orbiting the sun with a speed of, roughly speaking, 30 kilometers per second at a distance of 150 million kilometers, so 1 astronomical unit. The comet that is perihelion, the closest point of its orbit to the sun, is flying with a speed of, roughly speaking, 33 kilometers per second at 186 million kilometers from the sun. So this is a different energy level. The orbit has a different energy level. So what we had to do is to rendezvous with the comet. Well, it was actually nothing else than giving our spacecraft exactly the same energy level at the right position in space, at the right time as well, and then we would match the orbit of the comet. So what we did first time is to buy one of the most powerful launcher rockets that we have on the Earth. We bought the Ariane 5. It cost a few tens, if not hundreds of millions to buy it, and this rocket actually delivered us on this orbit. So it's a bit disappointing to a certain extent because we actually want to go to the green orbit and we are just on the pink orbit here, which is very similar to the one of the Earth. But actually Ariane 5 actually did a fantastic job. It basically flew us out of the gravity well of the Earth. The Earth is a massive planet, and of course with this gravity prevents us to go out. So we needed an enormous amount of energy just to go out of the gravity field of the Earth and fly around the sun on the same, more or less on the same orbit of the Earth around the sun. So then we started playing with gravity again, or with something else. We see later on what we did. We did a first Earth swim by only 1 year after launch. And this, we could increase the velocity of Rosetta at 1 astronomical unit from the sun because we were still coming back to the Earth, so this is 1 astronomical unit, up to almost 34 kilometers per second. So it's quite significant. You see, we are already exceeding the velocity of the comet, but we are much closer to the sun. The comet is farther away. It's loaded with potential energy that we don't have because we are closer to the sun. It's as if I drop 2 objects, one from this altitude and one from this one, when they land, they crash very differently because this has more potential energy. When it gets down, has a different level of energy. So then we did something that someone wouldn't expect. We are accelerating the spacecraft to actually enlarge the size of our orbit. And actually, this is what you see there is the orbit of Mars. This is the orbit of Mars around the sun. And we did actually what you see here. We actually flew next to Mars in 2007, and we actually reduced the size of the orbit of Rosetta. So in practice, in effect, what we did is we slowed down Rosetta. We gave Rosetta less energy. But why did we do this? Well, if you look at the pink orbit, the original orbit of Rosetta, this is definitely smaller than the one of the comet, but it's actually oriented more or less horizontally. The long axis is in this direction, whereas the one of the comet is in another direction. So we not only have to basically increase the size of the orbit, but also we have to rotate the whole orbit of Rosetta around the sun. And this is what we used Mars for, was to rephase the orbit of Rosetta such that we could meet again the Earth in 2009 in a very specific point. And this specific point actually allowed us not only to enlarge the size of the comet, increase the heliocentric velocity of Rosetta, but also started tilting a bit the orbit of Rosetta. So with this planetary swim by, we were actually playing with the orbital parameters of Rosetta in space. We did a third Earth swim by, and actually we finally went to an orbit whose axis is more or less aligned with the one of the comet. It's still a bit smaller than the orbit of the comet. There we couldn't do any more planetary swim by because on one side we were bound to the Earth distance from the sun. Our orbit was always going back to the Earth. So we had to increase this. And to do this, we actually did with maneuvers, with the rockets. We have on board the spacecraft, with the engines we have on board the spacecraft by using chemical energy. Chemical energy is stored in our tanks. We use them to fire these thrusters and actually have the 2 orbits matching exactly with each other. This is the rendezvous. We finally managed to set Rosetta on the final orbit. It took only 10 years to do this. To give you a feeling of what it means, Rosetta at launch had a mass of 3.1 tons, 3,100 kilograms. 1,700 kilograms of these were just propellant. For doing these two maneuvers, we used almost 1,500 kilograms of propellant. 1,500 kilograms of propellant just changed this tiny difference that was in the purple orbit and the green orbit. All the rest of the energy to get there actually came from the planetary swim by. If one computes the energy or the propellant we would have needed to actually fly Rosetta to this orbit, starting from there, we would come with a spacecraft, would have a final mass in the order of between 70 and 100 tons. You can spend as much money as you want, but you can't fly anything like that to a comet. So without those planetary swim by, it wouldn't have been possible at all to fly the mission. But yes, how do they work, actually? In internet, if you look for gravity assist maneuver, you find actually very easily this picture, which of course gives you an idea. Imagine you have a tennis ball, and you throw it against a train that is traveling against you, and the tennis ball bounces on the train and comes back with much higher speed. We actually transfer energy from the train to the tennis ball. But there's something odd. There is contact. When we fly in space, we don't have contact with two bodies. One will say, of course, you have a crash and you transfer energy, but when I fly Rosetta next to the Earth or next to Mars, I don't have a crash. I don't have this transfer of energy. So how does it work? Well, imagine of having a wooden plank, like here, and you put a metal ball on top of it. Then you pick up a magnet, and you put it under the wooden plank. And you actually drag your magnet. The metal ball is captured by the magnetic force, and then you walk, and you stop. And the metal ball shoots off. Who was given energy to the metal ball? Was it the magnetic force or something else? It was me moving. So gravity is not the one giving the energy. The energy is actually the ones of the planets flying around the sun. Gravity is just the medium we use to transfer this energy. The energy is the angular momentum of the planet flying in its orbit around the sun, and gravity is just the medium we use to transfer this energy from the planet to the spacecraft itself. What happens? We slow down the planet, we accelerate the spacecraft. So we actually cause a change in the orbit of the planet and a change in the orbit of the spacecraft. Given the different ratio of mass between the Earth and Rosetta, there's a big change of the orbit of the Rosetta, big change of the velocity of Rosetta, a very tiny change of the velocity of the Earth, or Mars in this case. We have actually slowed down slightly the Earth. The year, our travel around the sun is a bit longer after Rosetta did this flyby. I don't think we can measure it, but it's a matter of fact. There's no doubt about this. So this is the way, I say. So you see that we call them gravity assist maneuver. Yeah, we use gravity, but it's not gravity. Gravity is not energy. Gravity is in a conservative field. All the energy that gives you, it takes it back. If I'm Rosetta flying towards the Earth, actually accelerating me, people believe, oh, of course, it accelerates. But when it goes away, it takes everything back. All the kinetic energy that you have gained is taken back by gravity, and then it takes it back. So this is not really what counts, is really the movement of the planet, the flight of the planet around the sun. So having said that, now I give you a set of postcards of these 10 years in flight, these 10 years around the solar system. This is the postcard from the first Earth swim by. It was a fantastic achievement for us because it was the first time we were doing anything like this back in 2005. Then we flew next to Mars. You see a fantastic picture of Mars, and something that only, on the right side, you see something that only years later we basically came to the point to understand that this was a selfie. We didn't call them selfie at that time in 2007. This is actually taken as a picture taken 1,000 kilometers over the surface of Mars, and you see the solar panel of Rosetta sticking out. This is a picture of the second Earth swim by. This is our Earth at night. I apologize, I have to turn a bit. What is here is the Nile River. This is Spain. This is beautiful Italy. This is the UK with the coast of Holland. Unfortunately, I can't see Switzerland and Germany. Must have been cloudy, sorry. Then we flew, since we were flying in the solar system, and comets are a primordial object, as I said, also asteroids are, and since we were flying twice through the asteroid belt, we took the chance also to explore a bit the asteroid. This was the first asteroid flyby we did. It's called Steins. This asteroid was in 2008. It's a relatively small body. It's 5 kilometers big, more or less as big as the comet we then approached later on. And this we flew at a distance of 800 kilometers was the closest approach, but we just flew next to it and that's it. Then we did our last Earth swim by, and there was someone yesterday, for people that were here, say sometimes we should maybe look at formulas that we have developed in physics and just look at them and think about, reflect on them. Sometimes I think we should also look at pictures like this and reflect a lot on our Earth, on how much it gives to us. And on our travel as well, we flew next to an asteroid called Rosetta. This was much more massive, 130 kilometers size. We flew at a distance of 3,000 kilometers. And here we started practice some of the techniques that we used then once we flew the comet. We actually were, with our camera, following the asteroid. You see it in this video, of course, is when you flew next, and we were steering the spacecraft to track the asteroid. But we also did something else. The trajectory of Rosetta was slightly perturbed by this flyby at the asteroid. So the mass of the asteroid, the gravity around the asteroid, was perturbing the trajectory of Rosetta. We measured this perturbation, and we could infer the mass of the asteroid, and we actually could infer the density of the asteroid, which are all the data that our scientists are looking for. So it's something that we'll use later on at the comet. So here we are in 2010. Then early in 2011, we had to hibernate the spacecraft, switch it off, and abandon it for 3 years up to 2014. And many people believe that it actually took 3 years leave. Well, for me personally, these 3 years from 2011 to 2014 were the most difficult year of my career because we had to prepare something that nobody had ever even thought about, flying next to a comet. And this is what we did. So we came to 2014, and when we switched on our spacecraft, we started taking images in a portion of the sky where we more or less thought our comet would be. We started seeing something move compared to the stars. This was our comet. This was finally our target. There were a couple of things there. Well, first, we didn't know very well where the comet was. We knew more or less its orbit with an uncertainty of, roughly speaking, 10,000 kilometers. If you want to land on a comet, then you have to resolve this uncertainty. So the only chance for us was actually to do what we call optical navigation. You remember our orbit was a bit smaller than the one of the comet. So people believe that we came to the comet, huge brake maneuver, and stopped there. Well, it doesn't really work like that. In fact, actually, we were on a smaller orbit, so we were flying in front of the comet. The comet was coming from behind and was faster than Rosetta because it was on a larger orbit. So what we were doing with our thruster, we were continuously accelerating our spacecraft to catch up with the comet. Imagine, it sounds very difficult. It's not that difficult. Imagine you are in your car. You know that someone is coming from behind, and you want to proceed parallel on the motorway, and you just look in your rear mirror. You more or less, with your brain, by seeing the car moving in your rear mirror, you estimate the relative speed of the two bodies, and you actually press on the gas pedal. And when the other car is next to you, you have reached the same velocity. This is exactly what we did with the comet. We were looking at the comet, seeing how the comet was moving, estimating the relative velocity of the two bodies, pressing on our gas pedal with the thruster, accelerating Rosetta continuously, up to the point we actually came to the same point with the same velocity, same position, same time. So we had the same orbit around the sun. We had completed our rendezvous. These are the final days getting to this rendezvous. And I always say, flying 10 years in space with such massive planets, very well-known laws of gravity or space flight, you can call them as you want. It's like a bit driving on a German motorway. It's everything, there's a lot of energy, pavements are excellent, you know the rules, you perfectly know how to behave, and there's no doubt you get there, no problem. But when you get to an object like this, you will see it's like entering an Italian town. It's a completely different world. Many people say there's no gravity. We will see there is gravity around the comet, no doubt. But it's a completely different world. We didn't know anything. We didn't have a navigation system. There are no signs. It's exactly sometimes like driving to Italy. You have to get used or prepare very well for an experience like this. And this is what we did in our years of hibernation. So we actually had to understand the environment. So we had to characterize the environment in which we are flying, what we call characterize the comet itself. In space flight, we invented this very strange orbit that you see here. Actually, this is exactly what we flew on Rosetta, but we designed them in the years before. In space flight, when you want to set an object in orbit around another object, you have to know one fundamental parameter. The mass of the central body, in this case, was the mass of the comet. So we had to measure the mass of the comet itself. Otherwise, we wouldn't know at which velocity we would have to put Rosetta in orbit around the comet. So this is what we did, what we prepared for. I tell you already immediately, the comet is as big as the Mont Blanc. It's 5 kilometers big, it's ice and let's call them rocks. It's not really rocks, but it's as big as the Mont Blanc. It weighs 10 billion tons. This is the mass we determined. Sounds a lot. The density of the comet is less than half of water. If you put the comet in an ocean, it floats. Imagine the mass of the Mont Blanc or of the Earth. It's something completely different. So how did we compute all this? How can we fly in an environment like this? Well, now I start going a bit more technical, but since I was asked to talk about gravity, then let's talk about gravity. On this plot, on the left side, you have accelerations measured in Gs. For people that are less familiar with this term, just imagine a force. Technically, it's not correct, but it doesn't matter. And G, 1G, is the force with which we are attracted towards the center of the Earth here on the Earth, on the surface of the Earth. It's a logarithmic scale, so every step you go down is a factor 10 less. So you see it where it is 1e minus 0.6, means 1 million times less than what we have on the Earth. This is what we call microgravity. You have seen astronauts floating on the ISS. We call this environment microgravity. So 1 million times less. Technically speaking, again, is not correct. They are not subject to a constant acceleration, but the acceleration they suffer are in this region, 1 million times less than what we have here on the Earth. That's why they can float in the ISS. So let's see what Rosetta. Rosetta was on the right side, actually, I forgot. You can see the distance of our spacecraft from the comet, from the nucleus of the comet. And this was our plan. The green line is our projected distance when you saw these strange orbits flying, projected distance from the nucleus. We actually went down from a few thousand kilometers. Early August, we were supposed to be at 100 kilometers, then go to 50 kilometers, and then slowly down. The other curve you see there is what we call third body. Third body, we have the sun, Rosetta, and the comet. What is reported there, that value, is the difference in the gravitational acceleration suffered by Rosetta from the sun and the one suffered by the comet from the sun. So the difference between these two values is what we call third body. And to a certain extent, you can imagine this as the acceleration driving the relative movement of the two bodies. So as if the two bodies were not interacting with each other. But there's more. The comet was there. The mass of the comet was there. So how could we measure actually this mass? Well, we are left with this graph here. So let's assume something else. It's not anymore only the sun interacting with Rosetta. It's not the sun interacting with the comet, but also it's the comet interacting with Rosetta. The closer we went, the more we felt that there was something else than the sun pulling Rosetta. And actually, we could measure the central acceleration of the comet. So with this, there was a day, end of July, early August 2014, where we were a few hundred kilometers away from the comet. We started seeing the spacecraft moving differently as if we assumed the comet was not there. So with this acceleration, by measuring this acceleration, we could actually measure the mass of the comet, the famous 10 billion tons. But look at the values. We are far below microgravity at that stage. So we are actually measuring things which are more in the region of nanogravity. So this is the gravity that is around the comet. The actually dark blue line here is the gravity. The moment we measure the mass of the comet, we could project what kind of gravity level we would have on the surface of the comet, 10 to the minus 5. The Philae lander that was installed on Rosetta, this washing machine that was installed on the spacecraft, mass was 100 kilograms. On the surface of the comet, would weigh 1 gram if we were measuring weight at that stage. So this is what we projected as the evolution of the gravitational force or acceleration helping or flying Rosetta around the comet. Where we are talking about something below what the astronauts suffer or observe on the space station. But you have seen the comet. The comet is something that is very odd. It's an object which is like it's very porous, like pumice. Imagine pumice impregnated of ice. And when it's warm up, this ice sublimates and actually creates gas that goes out of the comet. And this actually creates something like is more or less like a wind. So we are left with something like this. But if this wind, you can imagine with the huge solar panels of Rosetta, this creates aerodynamic acceleration. It pushes Rosetta away. It's like the sailor at the beginning of the presentation. So not only we had to fight with such a small gravity, but we had to also compute aerodynamic accelerations acting on the spacecraft itself. We estimated them. They are in this order of magnitude. So they oscillate between picogravity and nanogravity. And we had to estimate them. We hadn't the faintest idea how they would look like. But we had to measure them to properly plan, to properly model the flight of Rosetta around the comet. So actually, when flying Rosetta, we were kind of measuring these accelerations and using this acceleration in our systems to plan the flight of Rosetta around the comet. Is that over? No, it's far too easy, like something like this. You have seen the shape of the comet. It's not really like a sphere. If we imagine the Earth, the gravity potential around the Earth is relatively uniform. Of course, we model all the oddities of our planet, but imagine the one of such an object. It has nothing to do with a sphere. So the gravity potential was changing completely depending on which zone of the comet we were flying over. To a certain extent, if we were flying over a mountain of the comet, we are actually suffering a different gravitational acceleration than we were if we were flying over a valley. And then we had to put also this variable into the loop. This complicated further the problem. Actually, the closer we went, the more we had to take into account these kind of odd accelerations that we were suffering on the spacecraft. This is still a component of gravity. Actually, it's the irregularity or the non-uniformity of the gravity field around the comet. And this is the black line. And you see that the closer we actually go down to the comet, the more this component becomes important. Well, we had to measure this one. For people which are familiar with the way the gravity potential is modeled, this is the second order harmonics. When at the end of the mission, we actually flew further close to the comet. We went down to 2 kilometers from the surface of the comet. We had to estimate the fifth harmonic of the gravity potential, because otherwise we wouldn't have been able to fly around the comet. So you see, with a spacecraft, we were measuring acceleration, gravity, up to the level of nano-Gs, pico-Gs, and we had to create model for this. Is that over? Not really. The red line here on the bottom doesn't play a big contribution in this phase of the mission. This is what we call SRP, solar radiation pressure. Is the photons emitted by light from the sun that actually hit the solar panels of Rosetta and push it away from the sun. Here we were at 3 astronomical units from the sun, where we were about to land. It's not a big contribution, but the closer we went to the sun, actually this acceleration was actually building up in value, and we had to take into account all these values in flying around the comet. So Rosetta was a mission no gravity. No, gravity, there was gravity, but the real problem of Rosetta was not the little gravity that there was around the comet, was all the rest that was there, because it was much more than gravity, much more difficult to model, and this is what we tried to do at best in our mission. So one of the most difficult operations we did for Rosetta was actually releasing the lander Philae, where gravity, of course, did play a role. People maybe don't know, but Philae was a completely passive, was a ballistic descent. It's basically, if you imagine the comet, like the Mont Blanc, I say this 5 kilometers big, the Mont Blanc is also 5 kilometers high, it's rocks, ice. So imagine you fly with an airplane, you have to actually land a washing machine on a glacier on the Mont Blanc. This is what we did in the end with the Rosetta. So we were flying at an altitude, in that case, of 22 kilometers. This is twice the altitude a normal airplane flies. So we had to drop a washing machine on a glacier on the Mont Blanc in a very low gravity environment. So that's why actually it took 7 hours for the lander to actually go down from 22 kilometers down to the surface. Actually, we did an accelerated descent, because only the gravity component, the contribution for this descent, contributed for an acceleration of the lander from 0 to 26 centimeters per second. So that's why we have been flying at 30 kilometers per second. Now we're talking about centimeters per second. The rest of the descent was actually Rosetta flying towards the comet, as you see in this graph here. Actually, we shot down the lander, then we gave it a small component to land down on the surface of the comet. What was difficult of Rosetta? Of course, all what I've said. We measure very, very tiny components of acceleration. And maybe the colleagues doing experiments, fundamental physics, these kind of things, they don't find these measurements that small. They are familiar with it. But there's one dimension of Rosetta that people maybe underestimate. We didn't have an instrument. Our instrument was the spacecraft. And actually, our spacecraft was flying in this condition. Imagine that the Earth is like a tennis ball. In this ratio, in this dimension, the moon is more or less like a boiled chickpea. If I take the comet, which is actually a bit smaller than that, it's actually like a very tiny slice of a tiny, very thin human being hair. So if you just cut a slice of one of your hair, this is exactly the size of the comet in this dimension. So these two bodies are separated by 380,000 kilometers, which in this dimension is 1.5 meters. So if I put here a tennis ball and a chickpea, I have the Earth and the moon. I have to place the comet. The comet was just at 500 million kilometers away, and this means 2 kilometers. So imagine that the comet is there. So this is where the comet was. But what we did, actually, control from a tennis ball in this room, we landed a molecule of hemoglobin on a slice of a human being hair placed on the broken chair at 2 kilometers distance. And this is where we had to measure, the condition where we had to measure all these values. And this is slightly different than doing it on a lab on the Earth. This was the real challenge of our mission. So now I'll let you with some more images. This is the descent of the lander Philae. I just give you a couple of information. Here you see the distance from the surface. This is animated in real time. If you were an astronaut on board Philae, then you would see the effect of the gravity of the comet on Philae going down to the surface exactly like this. This is the last picture Philae took before touching down to the surface of the comet. 9 meters. Next time you go out on the balcony on a 3rd floor, you look down the street, well, this is what you would see on the surface of the comet if you were on board Philae. This is one of the first images that basically Philae took on the surface of the comet. Of course, we didn't do all this to please us as pilots of something like this. We didn't do all this to measure gravity. We did this for science. And the scientist that is responsible for this camera on Philae once told me, this is the landing gear of Philae. It's 20 years old. The rocket that is behind, 80 centimeters away from the objective of my camera, is 4.7 billion years old. Is exactly what I wanted to see in my camera. And this is extremely rewarding for them. The mission, of course, was not over with Philae. We still flew next to the comet in this very harsh environment. We can actually flew very low on the surface. Here you can see the shadow of the solar panels of Rosetta on the surface of the comet. We actually flew in what we call snowstorm. This is the dust actually thrown out by the comet. This ice sublimating is cracking the surface of the comet and throwing these dust particles in the environment around, which was very difficult for us to cope with. But this is exactly what the scientists wanted to collect and see and analyze. So these are actually dust grains from the comet collected by the instrument on board Rosetta in this very odd environment. We saw flying boulders of 2-3 meters flying around the comet. We actually saw other effects of gravity. When we came there in 2014, one of the scientists said, I am waiting for the day this thing will collapse. It did collapse. Early 2016, we came there, we took these pictures, and we actually saw this wall collapsing. So there was an effect of gravity pulling down. It was a landslide on the comet. Here is an animation of what has happened on the surface of the comet there. So there is gravity on the comet, very, very tiny. So at the end of the mission, we actually looked very, very carefully. I don't know if you know the story of Philae. Philae actually landed on the surface of the comet. The systems that were supposed to anchor Philae on the surface of the comet actually block it there. It didn't work properly. We had a problem. And since the gravity field is so low, Philae bounced on the surface of the comet, flew up to several hundred meters of altitude and landed somewhere else on the comet. We could collect all the data from Philae because we had radio contact, so we could collect all the science data from Philae, but we could never see Philae on the surface of the comet till early September 2016, 2 years after its landing, where we actually managed to capture this picture, and in a corner there, in a crack, actually, you can actually see our lander, Philae. So this is what we have been doing for a few years. This is the last image Rosetta took before touching the surface of the comet. We actually landed the spacecraft itself on the surface of the comet at the end of the mission because we couldn't operate it any further. So we have collected thousands of data for our scientists. I hope they're really exploiting them as exactly they wanted. We had to fly in a very, very tough environment. We have learned a lot about low gravity environment. And it was not only important only for Rosetta. If you think about what a subject that in space is becoming more and more popular, we talk about planetary defense. We have NEOs, near-Earth objects, these asteroids, which are actually flying very close to the Earth, and their orbits are intercepting the orbit of the Earth. Well, one day will happen, an asteroid will hit the Earth. It has happened in the past, will happen in the future. But if we prepare properly, we actually understand these small bodies more, and we actually understand how to fly next to them. Well, maybe we can also prepare to defend our planet, our precious planet, from these kind of bodies. And I'm sure the Rosetta experience, flying in a low-gravity environment, flying in an environment like this, will actually help in this domain as well. Thank you so much. It's been an honor for me to talk to you. And the guy skiing on the comet was not me. I love skiing, but actually was a Photoshop. There was actually a guy skiing on a comet there. This was the surface of the comet with some ski tracks imposed on top of it. Thank you very much for your attention.
So thank you. Thank you. So thank you very much, Andrea Camazzo, for this really fascinating voyage. Please take a seat. As you know, we will have now a discussion. Before I invite the two other guests on stage, I remind you that for those in the room, there will be two microphones running on both aisles so that you can ask your question live. And for those in the room who are either too shy to ask a question live or have lost their voice due to cold, I remind you that you can ask your question through Twitter. This is also valid for all the people following us through the web, actually on their screen. They can also ask questions on Twitter, and all those questions will be relayed on stage by someone by Thierry Groisier, helping me with this task. So I have now the great pleasure to invite on stage two other speakers of this colloquium, Wright, namely Claudia de Ram and Thibaut Damour. Please join us. So before I come to our two guests, I'd like to actually first ask you a first question, Andrea. I was in Germany, in Darmstadt, where at the control center, where you were actually, but behind a glass wall. And I went back to the clippings I all kept for that day, actually. You can imagine, of course, that the Philae landing, I'm talking about the Philae landing here. Philae landing was all over the press. I mean, really, New York Times, I think we have a slide to show this. All over the press, and we could actually see you also on many pictures. You don't see that, but please have a look. You remember those pictures.
I remember them.
So we can see you smile, congratulate someone else, or even cheer. That's the low bottom picture where you're really cheering. I read all the articles yesterday evening, and I couldn't see a single quote of you.
A single?
Quote,
okay.
Because you didn't have, the occasion to talk to the media at that time. So now, imagine 4 years ago. What how did you feel deeply and personally?
It's funny because I had an expression when we landed Philae on the surface, but I'm glad most of you maybe don't speak Italian because I can't repeat it, and I won't repeat it tonight, but for people that speak Italian know what I'd say. No, as we were coming to, not to an end, because it was, in the end, if you look at why we do this science mission is to produce science. So at the end of the flight of Rosetta or Philae is actually the start of the Rosetta mission, because it's when we have collected the data, and the data is what we are looking for. But for us personally, it was definitely an exhausting period. We're coming to a point where we say, I like playing football, and we say, we have won the game this time. It's not only scoring a goal, but we were really, wow, we did it. And this is where I think all of us felt a bit exhausted. But we couldn't stop, we couldn't rest actually. We had to fly the mission for our scientists, and they wanted, as Catherine was saying earlier on, they wanted even more and more and more and more. So it was not that easy to manage all these expectations. But I think we had a good collaboration, and we were successful in this.
And tell us about Philae, because the joy was, perturbed like a little bit by this rebound of Philae. How did you experience that?
Well, it was professionally it was difficult to manage something like this, because when Philae landed, we didn't have enough visibility to determine properly its status. So we spent the night scratching our heads. The only thing we relatively soon understood was flying again. We hadn't the faintest idea why, and we hadn't the faintest idea where it was going to land. But the most important thing is that we maintain the radio contact. But as a person involved in operation, you have to imagine yourself as a pilot, and you have to sort of a bit lost control where your aircraft is, and it's not very pleasant. So there was also a part that was, of course, there was joy for the success, there was joy for having the contact with Philae, but there was also the frustration of not knowing exactly what was going on. And this is the big lesson learned we take out from that experience. And if we are to design other spacecraft like this, I think we should improve a few things.
Well, it lasted 2 years because you found Philae in 2016. How did it happen? Did you just put someone and ask this person to look at every image and look for Philae?
Well, in the end, yes, but we more or less knew where to look. The problem is that we were actually, with the comet flying closer to the sun, the activity becoming more and more. We couldn't fly anymore at 10, 20 kilometers from the comet. We had to go up to a few hundred kilometers distance because the environment was, let's say, not possible to fly in that environment. And from those distances, there was no chance. And that was also more difficult than expected because the surface of the comet was very corrugated in that area as well. Philae landed in what was the winter time when we actually went again close to the comet, so it was relatively dark. It was not that easy. But we more or less knew where it was because Philae had, of course, radios on board, radars on board, which were used also for scientific analysis. And by triangulation, when we were receiving the signal from Rosetta, doing triangulations, a bit the opposite of what we do what we do with the GPS, simply with the radio signals there, we actually could locate the area where Philae was, and then we set some people looking into every single image.
And what happened when someone found it?
Well, we already in May 16, there were some suspicions that this could be really Philae, but then we couldn't fly close to that area, only later in September. And one day, on a Monday, I got the news. I couldn't believe it. Also, the image is fantastic. You could see everything of Philae, the legs and the radiators, the solar panels, the antennas. So it was a unique day. It was the last present before the end of the mission.
Let me come now to our two guests and start maybe with you, Claudia. So you're working on very large distances, not on the solar system. And I'm sure you couldn't avoid, not following the media coverage of this mission. So what's your theoretical physicist view on that success? Oh, yeah, sorry.
It's impressive how well we understand gravity. I'm working on some models of modification of gravity, and every time you see how well we understand it, to those corrections, it's beautiful. It's such a fundamental theory, and I'm working on the theoretical aspect of it. So I'm used to just come up with numbers, 10 to the minus 20, etc. When you actually need to use these numbers and do something concrete with it, it's incredible that everything could go precisely as expected. All the corrections that you thought had to be taken into account were taken into account precisely at the level where you thought they should be. And it's amazing how well we understand things at those scales. It's mind-blowing.
Maybe same question to you, Thibaut Damour. So, for all of you who were not here yesterday, you're a specialist of the Einstein's general relativity theory and many other things like string theory, black holes, gravitational waves, etc. So, do you see any links between what you do and what Andrea is doing? And what can you take of maybe his experience or his
I must say that though I'm a theorist, I had many contacts with observations, real observations, both from objects outside of the solar system like binary pulsars, but also I've been linked with space missions. So I have incorporated the pleasure of knowing the beauty of all those missions and of having so many, crews of people making missions a reality. I admire very much the work of all the people from ESA, all the engineers, all the scientists that have given us so much beautiful data. Science, at the end, is based on ideas and on data, on experiments and observations. So it's an essential part also of my thinking about science. And I also remember the day where I heard that Philae had bounced, so I felt, I must say, anxious about this, like you. I said, okay, I knew it was a success, but still this thing was worrying for me too.
Indeed.
Can we also say that maybe a link unifying all of the three of you, and you didn't talk a lot about this, is maybe the quest of our origins. In your way, when we're talking about the origins of the universe, and in your way as well, because on comets are the cosmic travelers with signatures from the cosmic our origins, basically.
Well, on a different scale, of course, time scale, because we are talking about more recent times than what the colleagues are looking at, even though it's still a couple of billion years. And on a smaller scale, dimensional scale, but maybe we should actually ask Catherine this kind of question. But actually, what she's finding with their results as well is that what we find in the comet most likely is universal information. It's not only specific to our solar system, so actually it also goes in the direction the colleagues are looking, and that is actually looking, in the end, is always the same question: where do we come from, and who are we? It's exactly the same origin of the question.
And maybe another link might be the time that is needed to achieve such a mission. It took from the decision to make it?
More than 30 years. More than 30 years,
30
because
years?
in the first half of the 80s, this mission was conceived.
Yeah, and for you two, big theories being, drafted on paper, how many years, maybe decades or so?
Yes, also decades, but it's marvelous that human beings can ask questions and get answers about origins from, because 4 billion years or 10 billion years, the universe, this is similar, And over the last 50, 100 years, we have got many answers, okay? There are still many questions open, and Claudia is addressing some of these questions, but many answers.
You want to add something? No? Okay. So I propose now to just open the room for questions. There are many. I hope I will see you better than yesterday evening, because I have strong light. Yes, thank you very much. So this is better. So there is one here. Yes, please. There's one. The microphones are coming. So again, all of you following us on Twitter, please ask your questions as well, and we will relay them. Yes. Oui, c'est bon.
Merci. The question for Andrea. You mentioned in the beginning that there are millions and billions of comets. And a few questions. Why did you pick this one specifically? The second question is, given the distance, how long does it take for the radio waves and the information to go back and forth from the Earth to the comet and back? And the last question is, how long will the system now work for how many days, months, years you expect Philae to collect information and send it to the Earth?
Okay, why this comet? First, we could only select comets that are really trapped in the inner part of the solar system, because are the only ones we can reach. For example, in '86, there was the Giotto mission that flew next to the nucleus of Comet Halley. This Comet Halley has a period of 72 years. We could actually fly next to its nucleus for a couple of hours, cross the trajectory, but nothing else. We would never be able to go on an orbit like that. So we had to, these are called the Jovian comets, trapped in between, roughly speaking, between the Earth and Jupiter. So only this was the family of comets we could actually reach with a mission to do what we wanted to do. Why this specific one? Well, there are classes of comets in terms of activities. We didn't want to go to a comet that was too little active, because then you don't see the material that is coming out, which is exactly what we want to explore. We couldn't go also to comets which are far too active, otherwise we wouldn't have been able to go that close. Then you have programmatic aspects, when you can actually be ready with your spacecraft, what your launcher can do, what the propellant you can load on board. And then by analyzing various trajectories of different comets falling into this class, we found out this opportunity. Actually, Rosetta was supposed to be launched in 2003 to fly to Comet Virtanen, another comet. Then due to a problem on Ariane 5, all Ariane 5 were grounded. We couldn't launch in 2003, and we had to look for another comet, because in the meanwhile, not only planets have moved, but also the comet had gone somewhere else. So we actually found this opportunity. The radio wave, of course, this is purely depends on the distance between the two bodies. The day we landed on the surface with Philae, the propagation delay one way was, roughly speaking, 30 minutes. So 30 minutes to go and 30 minutes to come back. And Philae was active for 3 days on the surface of the comet. So in 2014, this was the capacity of its own batteries. Then was supposed to go on an extended bonus mission with the solar panels that were installed outside, but unfortunately landed in this cave, and it couldn't work. Only when this region of the comet, where it actually came to rest after landing, went to its own summer, Philae was lit again by the sun. It woke up and started retransmitting a few data to Rosetta, but was somehow damaged, and we could never actually control Philae itself. We received for a few weeks some data, engineering data, not science data, which are still valid for science because we get temperatures and what we were observing on the comet, but we've never been able to command Philae anymore. So Philae is dead actually since 2015.
Let's dig a bit on this cosmic flipper, as Thierry called it. How do we have to imagine this? Do you just target a comet, then press enter on the enter key on your computer, and you have a trajectory, and you then have all the flybys provided by the computer? Or how does it? Okay. How do you manage to find the right trajectory, multiple trajectory actually, to the comets that you chose?
Well, it's of course computer help a lot in everybody's job nowadays, but without the human being behind driving them, you don't go very far. Our typical project, what we call mission analysis, actually, is the process we use to actually define the trajectory of a space mission. Is we actually normally start from the endpoint and we work backwards. So we know what, in this case, we knew the orbit of the comet, more or less, and we started working backwards, what kind of energy we need to be there. So how can we get to that energy level? So working back, and maybe we could do an Earth swim by. So we can actually roll it back up to the point where we can see what is at the end, whether it's still feasible, whether we can launch a spacecraft with that mass. We have just launched Baby Colombo. The process is very similar. We can arrive at Mercury. We could arrive at Mercury only in very specific seasons of Mercury under specific conditions. So we have a few points in time where we can start working back. We actually used various techniques. And of course, this is where the computers kick in. They actually analyze and optimize the single elements of the trajectory. But who puts together is an artisan, if you want, of this job.
But the computer is very intelligent and found like tens of solutions, right? How did you choose the right one?
Well, of course, then we're not tens in the case of Rosetta. We're a few, not many actually. But then you look at the duration of the mission, where some other parameters, constraints. For example, you might have long eclipses and your batteries cannot afford it. Or you might have to do maneuvers or critical phases in conditions where maybe you are seen from the Earth, you are behind the sun or close to go behind the sun. So this is not ideal because you are about to lose the radio signal for a couple of weeks. So there are these kind of constraints that you start eliminating trajectories which are not as ideal as others.
Let's go back to the room. Yes, there is one question here in the front. S'il vous plaît.
Thank you. My name is Roberto. I remember what you said during the landing, but I understood what you mentioned. My question is more related to the opportunity of failure during space. I remember Luca Parmitano almost drawing years ago. I remember the ExoMars Schiaparelli landing that somehow we lost. And I know that there were some problems about the bouncing of Philae. So my question is more in a positive sense, saying, how important is to fail during space and doing science? It's more related to all of you, in fact. Thank you.
I think it's fundamental. If we are not prone to risk, we are not prone to failure, we don't go anywhere. We actually would stay in our environment, which is very comfortable. So it is an inherent part of what we are doing. Then what our job is, more than the scientists, is this risk management. This kicks in as well. Once you have to implement the project, you have in the end, you have a huge responsibility. And in looking into these missions, we have to analyze all the aspects before we make a final decision. It's one of the most challenging part of our job. It's also one of the most fascinating, because in the end, most of the time you have to make a decision without enough information to make the decision. And this is what puts you really in front of reality. But failing, it has to be part of the game. Otherwise, we'll stay here on the Earth.
Well, failing in your case means a crash or a loss of the spacecraft.
In the case of Schiaparelli, it's a crash. But Schiaparelli, we did it for as a demonstrator for our next mission, which is a rover. Yeah. That one we cannot crash. And if we crash, that one is a real failure. Schiaparelli was a test and would have been a failure if we hadn't understood why it failed and we wouldn't be able to fix. Then it would have been a total failure. I think of course, there is a failure component to what has happened, but the real failure comes if we fail the next mission. Then it's a failure.
So there's no crash in theoretical physics, right?
There's no crash.
What does failure mean?
Yeah, well, I have to say, every day when I wake up, I know I'm going to fail. A few things that day. I'm doing mainly theory. And you try, you have to try, and 90%, I would say 99.9% of the ideas we have, the things we're trying, they will fail. We know they will fail, and we don't know what the right answer is. If we knew what it was, if we knew how we should start so we get to the right answer, then we could ask a computer possibly to do it. The whole part of our research is the creativity, and with that comes the failure as well. Just like you have to imagine if you're a painter and you think you have a vision of what you're gonna paint, and at the end of the day, maybe it's a success, maybe not, and you can't tell whether it's going to be a success before you actually have implemented it and went through. And even if you think it has failed, at some point maybe you have to sleep over it for a night, for a year, for 10 years, and maybe you come back and you realize, that's actually what was missing. Maybe I need more color here, maybe I need that ingredient. You need to discuss with colleagues, and then it's an ongoing process. But every day you try little ideas and you realize that actually that's not the way it works. It cannot work that way. Or you realize you haven't understood things to the deep level that you should have done.
I just wanted to cite in this respect one of the greatest mathematicians of the 20th century, Alexander Grothendieck, who said that indeed to find the truth, you have to be very close, not to be afraid of the error, of making mistakes. That's when you are close to and not afraid of the error that you can find really new things.
Maybe a similar question is, the fact that we could see everything, right, with your mission. We could see up down to the ground of the comet with Philae, etc. This is much less the case in cosmology and astrophysics. Actually, your story was all over the press worldwide. And recently there were two really major discoveries about the black hole that stands at the center of our galaxy. And the coverage was really much lower. What is your view on this? We cannot see things in cosmology and theoretical physics. Is it harder for you to, for example, get to the media? I was talking yesterday to a journalist from the local television, and she told me I was struggling to promote a 2-minute item in the 19h30 chez Darius. It was difficult for her to promote this really major story about our black hole. So how can you explain that? Is that just that we don't see things?
You're right. It's a concern for anything which is a little bit too abstract. I mean, scientists can see the beauty of abstraction, but the general public cannot be attracted to this. So, but it's important for the whole of science. I mean, the fact that there are parts of science which are very visual and attract a lot of attention is a big benefit for the rest of science, because people know that beyond our everyday concerns, there are some strange people, scientists, who spend decades, tens of years trying to understand mysteries of the universe, and we are all part of a community, so it's good for all of us.
Even within the agency, we have obviously space missions which are far less appealing or much more difficult to explain or to sell to the public than Rosetta. And I always said we should use the success of Rosetta to explain also the success that is behind all the other missions, because maybe they are even technically and technologically more challenging than what Rosetta was, but it's much more difficult to explain them. And we have to exploit these, not beyond the agency, of course, but also in other areas. We have to exploit these successes.
Yeah, one example of this is the mission Microscope, which is now flying above our heads, which also took many tens of years of preparation and existing. And it is testing whether all bodies fall in the same way in a gravitational field, an idea of Galileo. And indeed, it is less visual. I mean, it did not make much news, but it has a fundamental interest. Yeah. So.
Well, but still, when preparing, keep the mic. I have a question for you. When preparing this evening, you told me I would like also to link our three stories to talk about irrationalism and you quote it this way: fragility of science when the public doesn't understand it anymore. But here, when you saw those images, I mean, we understand that. We go there, we see what we're doing, and we understand what we're doing it. So would you maintain your sentence?
Yes, but the danger is there. For instance, I would recommend everybody to read the very important book of Lucio Russo called La rivoluzione dimenticata, The Lost Revolution. It's not even translated in French, it's in Italian and in English. And this is about the end of the Greek science in Alexandria, which was very abrupt. I mean, we lost many things because, I must say, the Romans did not care about science and very theoretical science. They killed Archimedes and they burned most of the books. And then the beginning of Christianity decided science was bad and things like that. So it means that in a few years, actually, we lost big developments. And for instance, a fantastic artifact is the Antikythera mechanism, which proves that the Greeks had attained a very high level of technology and science, which was lost in 10 years at the end. So, and today, the fact that many people use the beauties of the technological applications, but sometimes they identify science too much with applications, like they say, how do you say OGMs in English? GMOs, no? Genetically modified things, and nuclear power. I mean, they think science is bad because of this, because they don't see always the conceptual aspects. So seeing only the visual aspects is good, but helping people to appreciate more conceptually science, I think, is very important.
But more broader, would you say, Andrea, that your mission, let's call it your mission, helped, in these times now of fake news, of mistrust in science, in news about science as well, that are getting more and more important, that this mission helped show the importance of science in society? And this is a question for you.
I'm sure there are people doubting that we landed on a comet. I have no doubts. Nevertheless, I still want to do my job. I hope it helps. I'm convinced it helps. I think what this mission could transmit was this very direct, very close contact with public. What people could see also, passion people put in their effort, the scientists, we engineers, and everybody. And in the end, if you look at behind all what we do, we are like an engine, and the passion we put is the fuel for this engine. If you just remove the fuel, your engine can just stop working, and we don't go anywhere. So this will help in this direction. This is my lesson, the lesson I take out of Rosetta.
And you two, how do you navigate this world of mistrust in science?
I mean, one excellent aspect of Rosetta, for instance, even though it's more visual and people can connect a little bit with it, it's not going to have any implication for tomorrow. And if at the very least people can connect with that, appreciate the beauty of just understanding, pushing our knowledge further, just because that's who we are and that's important to keep, and not because there's going to be an application, there's going to be some funding coming out of it for tomorrow, is very essential. It is true, and then there's layers of how abstract it is, and if we're dealing more with black holes at the center of a galaxy, then it becomes more abstract, and we don't have as many cool pictures. A black hole would be hard to take in picture, and is associated with many abstract concepts which people don't necessarily feel comfortable with. But it's also our job to make that communication, make people feel more comfortable with that. And I mean, the vehicle is there, the bridge is there, we just need to go further in this direction.
Thibault, you want to add something? No?
No, not now.
No. Very last question before I go back to the room. You were named in 2014 one of the 10 best scientists by the famous magazine Nature. It's not about your naming one of the 10 best, but about having maybe stars in science. Do you think, like in music, like in literature, like in every other field, do you think that science lacks stars?
I think it lacks this, and I think it deserves something like this. I felt extremely rewarded. Definitely, I would lie if I were to say the opposite, but embarrassed for all my colleagues that have basically worked exactly as I did, and I was named in this article. But I think science lacks something like this, and we should put a lot of effort in this direction, in communicating properly and getting scientists much closer to public, such that they can actually interact much more. And this is, for me, is the key for the future.
So you want to?
Yeah, and one person who lost recently, who played a very important role in this respect, was Stephen Hawking, because Stephen was both an undisputed, very deep scientist who had discovered something extremely important, and then for years he used, also the fact that he had a especially bad physical condition, he played a little bit with this, but always in a sincere way. And he played a very useful role for communicating the beauty of theoretical physics to a very large public.
So let's interact. Are there more questions? So one here, and then on Twitter. So Monsieur ici. And then d'abord ici, et après je vais chez toi. Yes.
Thank you. I would like to ask a question about the comet. There was a paradox in what you said, so it's a simple question. On the one hand, the comet is billions of years old. On the other hand, it's losing water, it's losing ice, it's losing mass. How do I reconcile these two things? Is it also accumulating mass from somewhere else? Or is it just much smaller than it was?
Definitely, it becomes smaller and smaller. The closer they are to the sun, the more mass they lose. Our comet will take quite a while before it's exhausted, but actually the mass being thrown out by the comet itself is actually what the scientists can analyze from remote. The instrument of Catherine, for example, is analyzing what is coming out from the comet, the gases that are coming out, so all the material that is coming out. And also what it does by being sort of, let's call it eroded, even though it's not an erosion process, but being cracked, it reveals the pristine material that is inside the comet. The outer shell of the comet, for this comet in particular, that is inside the solar system, is a bit processed by the sun itself. There are processes where ice sublimates, then resublimates, and so then it's a bit processed material. Whereas with this sublimation, when there are these big cracks, they actually reveal the pristine material of the comet. This is exactly what the scientists want to do. At the end of the mission, we actually landed Rosetta very close to a pit. So like a crater, it's not a crater, it's not bombardment, but collapsed surface of the comet, because they wanted to look that, because it was very recent material, inner material of the comet exposed. So it's exactly what the scientists wanted to do. One day the comet will fall onto the sun, no doubt.
Thank you.
So let's go to Twitter for a few questions, if there are some.
First, just a remark on the discussion of before. There's a glimpse of hope in the fact that people are interested in abstract science just by measuring the public we had yesterday. A very abstract subject, and people come. So I think we have to be a little bit careful when we just want to sell science as a set of nice images and say that that's what the public wants. I think the public is more sensitive to that. We have to work a little bit on that, but this interest is there. Now, this interest is maybe dampened a little bit by the question that has come through Twitter, which just asks, how much does it cost?
So the mission, as funded by the agency, has costed, roughly speaking, 1 billion euros over maybe 20 years, let's say, 20 countries. Plus, we estimate there must have been 400 million euros invested for the science instruments, which are funded by national agencies. I'm a super fan of football. We pay one football player 200 million, and we don't pay 1 billion for Rosetta. There's something wrong.
There is also something very interesting in this number of 1 billion, because it's all work, actually. You pay really work. A man-year, whatever you need to call it nowadays, but a man-year costs about 100,000, give or take a factor of a little bit. So it means that actually to make a mission like that, you need 10,000 man-years. So either you put 5 people since Jesus Christ, and you do get your 10,000 man-years, or you put 1,000 people for 10 years, and we've learned how to do it. And there's something rather deep in the way in which the society builds itself out of this number of 1 billion, if you take it like that. I mean, you can also compare it with coffees and things like that, but just look at what it means in terms of societal organization is something which is extremely useful, I think.
Indeed.
So 1 or 2 more questions. Yes, one there, please. Merci de lever la main.
Yeah, so my question is as follows. When we landed on Philae and we obtained science data, your stated goal was to better understand how our solar system formed. So what did we learn in that respect?
Okay, we have learned a few things, which I actually relay from Catherine. She's been feeding me with information because I'm an engineer. We found molecular oxygen in the nucleus of the comet. And I'm told, because it's not my domain, that this is extremely reactive. So this thing, if it was there during the formation of the solar system, would have reacted immediately. It's very reactive. So it means that it was trapped inside the nucleus of the comet before the formation of the solar system. And that's why I said in my presentation, we thought maybe comets were the remnants of the formation of the solar system. By knowing that this molecular oxygen could have not survived the formation of the solar system, we understand that comets must have been there already before this formation of the solar system. So this is already an information. They found basic amino acids. Amino acids are the bricks, the building bricks, if you want, of proteins, which are the building bricks of life. And if they were trapped inside the nucleus of the comet, together with oxygen, and these both elements or components were trapped in the nucleus of the comet before the formation of the solar system, Catherine tells, but these are not specific to our solar system. The building blocks of life are actually most likely universal. And we learn something about our universe. So it could well be that life has formed or spark also somewhere else because of this. So these are the things the scientists are learning. Catherine, correct me if I'm wrong, but you know much more than me. Okay. So this is what we are learning.
Catherine Altweg, you have 2 minutes to summarize what you found during all those years.
Well, we have found a few more things. That there is still the question where the Earth got its water, because the Earth was very hot at the beginning, no water at the surface. There was a theory that comets should have brought that water. We could find out that this is not true. So the terrestrial water is not from comets, but we also know that most probably part of our atmosphere, especially the noble gases, are cometary. The xenon in our Earth's atmosphere is exactly the same as the xenon in Churyumov-Gerasimenko. And that tells us how much material was actually delivered by comets. It's about 1% of our terrestrial surface water. But it's a lot of carbon-bearing species, because we found a mass of organics, not only amino acids, but ring molecules, benzene, naphthalene, alcohols, a lot of stuff. And this could actually have sparked life. So if you throw a comet into the Lake of Geneva, it will melt. The molecules will react with water, and that's maybe how life started on Earth. And as he said, comets are not older than the solar system, but the grains which made up the comets are older than our solar system, because they contain oxygen, they contain S2, which is also very reactive and would have disappeared if it would have been in the gas phase. So we know that this material is actually universal. And I think that's
Thank you.
A big step forward.
Thank you very much. So time is running fast. One or many questions from Twitter, and then one last question from the audience.
One question, actually, with all due respect to Catherine, it is easier to analyze the material of comets in a laboratory than it is to do it in situ. So the question is, can we bring back material?
It's not true, it's not easier, because you have to bring it back cryogenically at 20 Kelvin. And that's, I think, technically at the moment not feasible, because you have to go through the Earth's atmosphere, and this will most probably destroy the material, and then you have to pick it up in the desert somewhere on the Earth, and you cannot keep it at 20 K. And then you don't have the material you had on the comet. So you have to go to the comet and do it there.
So one last question in the audience, if there is one. Otherwise, it will be mine. And you know now that I like to close those sessions by a quote. This quote could have been Neil Armstrong's quote, because we're getting close to the 50th anniversary of the moon landing. But it actually has been rephrased by Jean-Jacques Dordain, your former boss, actually, at ESA. That's the Director General at ESA until, 4 years ago?
2
2 years ago?
3 years ago.
And he said, paraphrasing Armstrong, it's a giant leap for the human civilization when Philae landing. So he was your boss, so you must agree, but do you?
Yeah, I agree. I think the part I like most of Rosetta is that this mission was conceived in the early 80s by scientists that knew they wouldn't be there when Rosetta would have been implemented. Nevertheless, they gave the go for something that they would never see. And this is something we should carry in our as a lesson. I think we should also project us to the future and be less egoist and look a bit further out in the future. Nowadays, with these mobile phones, everything is obsolete after 2 seconds. A 30-year project, we don't embark on it anymore. And this is the lessons I learned from Rosetta. These are the giant steps, the giant leaps that we can make in our society.
And what are the lessons that you take from this? Is that a giant leap? Yeah.
I was just about to think, I'll tell you that tomorrow, right? Because I can give you a preview, but it's not going to be a happy Hollywood, happy story, happy ending. And I think it's important because that's the way research works. That's the way sometimes science works, and that's the truth. And it'd be nice just to present you every time a happy story, Nobel Prize winning in the end, but that's not reality always. Sometimes it is, but not always. And we go, again, through many failures, and we go through open questions, and it's going through them over and over again that we really progress and get to where we are.
Yeah, a similar time scale was for the work on gravitational waves. I mean, Joe Weber had the idea in 1955. I remember meeting him as a young postdoc. I was 23, and everybody was attacking him because he had claimed the discovery of gravitational waves, but he pioneered the thing, and then it started, LIGO started, Virgo started, so all that, I was involved trying to push the thing, so indeed, I mean, all that took many, many years, and with success, and some of the people who started that were dead when the experiment finally discovered gravitational waves. So mankind has the power of projecting itself in the future. So
you're talking about time. Our time is gone, so please thank our 3 speakers for tonight. Voilà, permettez-moi de conclure en français, simplement en remerciant toutes les personnes qui ont contribué à organiser cette soirée, tout le colloque, la Fondation Wright, l'Université de Genève, Thierry Courvoisier et ses équipes. Il me reste plusieurs choses à vous dire. D'abord, de venir, bien sûr, en vous invitant aux autres conférences de cette semaine, à commencer par celle de demain de Claudia de Ram, demain soir, même heure, même endroit. Et pour ceux qui ne l'auraient pas encore vu, d'aller au Parc des Bastions, il y a un fantastique spectacle dont on devrait voir quelques images maintenant. Tous les soirs jusqu'au 21 novembre, 18h, 19h, 20h, ça dure 20 minutes. Le bâtiment principal du parc est habillé par un spectacle son et lumière. Allez le voir, il paraît que c'est fantastique. Merci à vous et à bientôt. Bonne soirée.